Project configuration, setting up core spanning tree. By the time we're done here, you will understand and configure spanning tree protocol like a ninja. Now, we've been talking about spanning tree protocol through this entire series, but before we go in and configure it for our customer, I want to do a brief concept review because I found this is one of those concepts that just doesn't stick in people's minds until you've seen it a number of times. Spanning tree protocol is designed around the fact that redundancy is good. Single switch connections means a single point of failure. If I've got switch 1, switch 2, and switch 3 in this picture, and this cable breaks, then all of the clients attached to switch 3 can no longer access the rest of the system. That's not good at all. The good news is that it's very simple to create redundant links. All I need to do is plug a cable like this, or a cable like that, or something like that to eliminate that single point of failure. But if I do that without spanning tree engaged, I can cause a loop that takes down the entire system. That's because a switch will send a broadcast packet out all ports. And computers send broadcasts. That's just what they do. Switch 3 would receive that broadcast, send it out these ports. Switch 2 would receive it, send it out this port, and switch 1 would receive it and send it out this port, and this one would cycle through and come out these ports, and it would loop around the system thousands of times every single second, taking the entire thing down. Not only the switches receive that, but every computer, WAP, server, everything that's plugged into the network gets barraged, and their processors shoot through the roof. It's known as a broadcast storm, and I've gone through a number of them in my career, and they've never been good. It is a business down situation that if you can't find that loop quickly, typically ends up with everybody being sent home and the company closing for the day. It's really bad. So Spanning Tree Protocol steps onto the scene to allow you to have your cake and eat it too. Allows you to have your redundancy, but stop the broadcast storms. So let's bring our redundant link back into the picture and label our switches. The way Spanning Tree works is by picking a center of the network, and that is known as the root bridge. All the other switches will then find the best way to get to that center of the network. And they do that based on the cost. And as we would expect, the cost is a direct relation to the bandwidth of all of the links. Let's just say that these are all 1 gigabit per second connections. Well, that has a spanning tree cost of 4. I'm going to show you a table in just a second that shows all the common link speeds and what the spanning tree cost is. So if this guy's the root, then switch 2 says, okay, well, what's the best way to get to the root? I could go this way and it's a cost of 4, or I could go to the right through switch 3 and it's a cost of 4 plus 4. That would be a cost of 8. This is definitely the best way. I'm going to call that my root port. Switch 3 does the same thing with the same characteristics. It's going to look and say, okay, well, this is my best way. That'll be my root port because it's only a cost of 4. The other way would be a cost of 8. Once they've picked their root port, the switches then look at all the redundant links, all of the backup ways to get to the root bridge, and realize that those could be loops. So they block them. Now, how do they find all these redundant paths? Well, that's the job of the BPDU. Think of that as spanning tree sonar. Boom, like a submarine. Switches send BPDUs once every 2 seconds by default. And they send them out every single port, even ports that connect to computers. And those BPDUs go around the whole network. And when a switch gets its BPDU back, it goes, it's a loop. This is mine. How did it get back to me? And so the switches are able to figure out what the topology looks like, what all the switch connections look like, through this constant sending of BPDU sonar. So once switch 2 and switch 3 have figured out their best way to get to the center of the network, they block the redundant paths. Now, this is a really high-level overview. As with all things networking, there's a lot of nuance inside of this and a lot of nitty-gritty detail. But from a conceptual level, that's it. So in order to be effective in Spanning Tree, you have to dive into a little of that detail. You have to know how Spanning Tree works. For example, how does it elect the root bridge? That's a pretty important decision because that's going to become the center of the network that everything goes through. Well, the way it does that is by picking the switch with the lowest bridge ID. And I'm sure you look at that and go, okay, what's the bridge ID? Well, the bridge ID is the combination of two things. The bridge priority added to the bridge MAC address. And I'm sure right about now you're going, Jeremy, you're killing me. What does this mean? What is the bridge priority and the bridge MAC address? Good question. And now we're getting to something real. The bridge priority is just a number between 0 and 65,535. And it just so happens when you pull a switch out of the box that's running Spanning Tree Protocol, it will have a default priority of 32,768. And don't worry, when you've seen these numbers 100 times, you'll remember them too. Keep in mind that Spanning Tree Protocol is an industry standard. So if you claim to be an industry standard switch, you have to abide by these rules. The bridge MAC address is just the MAC address of the switch. Every switch has its own MAC address, not just the MAC addresses that it's learning. It has one that it belongs to itself. So all of these switches will take that bridge priority. Let's just say it's at default. This switch, we'll call it switch 1, has the priority 32,768. Then it says dot and puts its MAC address. 1234.1234.1234. Now I'm putting the dots in there because it's easier for us to see. But in the switch world, it's just one big long string. The root bridge will be the switch with the lowest bridge ID. So let's say this guy is switch 2 and follows a similar pattern. 32,768 default priority, dot, and then its own MAC address. We'll call it 222. And we've got switch 3 in the same situation. And let's add our redundant link back in. When these switches power on, they all send BPDUs to each other. Now, I told you before, that's kind of like Spanning Tree sonar, how they detect the loops. But I want you to think of those BPDUs like an envelope. Inside of that envelope is their bridge ID. So that BPDU is also how they participate in the election. All the switches exchange messages back and forth, and the one with the lowest bridge ID gets elected. In this case, that'll be switch 1 in the lower left. That's how the root is elected. So let me clear all this off and draw back in the essentials. Now all the other switches find the best path to the root. I mentioned on the previous slide that they're going to do that first off by finding the lowest cost path. Cost being a direct correlation to how much bandwidth is on those links. I mentioned a moment ago that 1 gigabit per second links have a cost of 4. And that's how the election worked on the previous slide, is all these things said, okay, everything's 4. This is the best way. That's my root port. This is the best way. That's my root port. And this one ends up getting blocked. So the end result looks a little different from the previous slide, but that's just because the switch in the lower left is now the root bridge instead of the one at the top center. What I want you to see is that does affect which links are active and where all of your traffic flows. Your root bridge should be the biggest, baddest switch on your network because all the traffic's going to go through it to reach each other. It's the hub of your system. Now, if you had a different speed link in your network, like let's say this is a 10 megabit per second connection, that will immediately impact your best path calculation. Instead of a 4, a 10 megabit per second link has a cost of 100. And now switch 3 says, whoa, this is the best path because that's a total cost of 8 versus a cost of 100. This link is really active, and this link ends up being blocked. So you can see that cost is a huge impact when it comes to which links are going to become the best one. But what if the cost is tied? I mean, what if you had a situation like this where you had switches connected in a little triangle right here? This is your root bridge, and this switch down here is trying to figure out the best way to get to the root. Well, if all these are 1 gigabit per second, it's looking and going, okay, well, I've got 2 equal cost paths to get there. I can't have that. I need to block one of them because it's going to cause a loop, so it fails over to the second algorithm in our list here, and that is the lowest bridge ID. Meaning, we know in the network as a whole, the root bridge has the lowest bridge ID. That's how it became the root. But these guys also have bridge IDs. They're not lower than the root, but they will be different. So this switch will say, okay, I'll pick the switch that has the lowest bridge ID. Let's just say that's switch 2. Switch 3 has a higher bridge ID, and that link will end up being blocked. But even with that, you may end up in situations where you have a tie. And that's where we rely on number 3. The lowest port number breaks the tie. You might be thinking, what does that situation even look like? It'd be something like this. Switch 1 connected to switch 2, and you take cables and go chunk, chunk. Equal speed, so the cost is tied. Same switch, so the bridge ID is tied. Now you've got the port number that breaks the tie. The one with the lower port number, let's just say that's port 1, wins. The higher port number gets blocked. I know this has probably been a little bit more concept than you've been used to, but there really is a lot of nuance to Spanning Tree, and when you're trying to track down a loop, understanding spanning tree is essential. So let's take those concepts and apply it to our network environment that we've been building. Hopefully you've been going through this series in order, so this messy looking topology makes sense to you because we've been building it as we go. Now, early on in the series, we identified that switch number 1 in suite 1 should act as the spanning tree root bridge. We just didn't do anything about it. It was just in theory, and now we're at the point where we can configure it. So I really want to make that root designation right here before we go any further in understanding our spanning tree design. So let's bring a web browser up and go to that 10.225.1.240, which really is that switch number 1 right there, .240. Get logged in, and I'm going to shoot over here on the left-hand side into that spanning tree world. Now, the first section right here is STP status and global settings. And we see a laundry list of options going down the screen here. First off, you can see spanning tree is turned on. That is the default state for most managed switches when you pull them out of the box, because there's probably very few vendors out there that want to be known as the vendor that caused the loop in the network. So they all turn on spanning tree by default. Now, there are 3 different modes of spanning tree. Classic, which is old and slow. Rapid, which is newer and faster, and multiple spanning tree. And that is where you can run spanning tree on different VLANs differently, and we'll explain that when we talk about VLANs in a totally different series. There's plenty of other options, but what I want you to see here is the bridge priority. Notice this guy is 32,768 because it's an industry standard switch out of the box. Now look at this. When we look down below, we see the designated root bridge, or designated root as it shows in the GUI here. It says the bridge ID is this, and that is this switch's bridge ID, meaning 32,768, that's the priority, tacked onto the MAC address. And it's saying the switch that's the root of the network is this, which, looking at it, happens to be exactly the same. We didn't intend it this way, but this suite 1, switch 1, just happened to become the root bridge. In the roll of the dice of 5 different switches in the network, it happened to have the lowest bridge ID. We had a 20% chance and we won. But I want to show you what it looks like from a different switch's perspective. Let's take a look at this switch over here in suite number 4. We'll get logged in to .242. There we go. And let's drop down to spanning tree over here on the left. And if I scroll down a little bit more, I can see this guy has the default priority of 32,768. But look at his output. He's saying my bridge ID, this is me, is this value right here, and the root bridge ID is this value right here. Now we see that they're different. That root bridge ID happens to be switch number 1. I just click the tab over here to switch 1, flip back over to switch number 1 in suite 4, and we see the difference. Now you see right below that, the root port is gigabit Ethernet 28. Let's look at the diagram. That's exactly what we expect. 28 is the one that connects back to the root bridge, so that's going to be the most efficient way, or should I say the lowest cost way, for it to reach the root bridge. Now if we come back here, we see the root path cost is 20,000. Now wait a sec, Jeremy. I thought you told me that the cost of a gigabit per second link was 4. Well, I did, and that's because I used the widely accepted classic spanning tree cost table. See, I just did a quick Google image search for updated spanning tree cost table. And you can see the first link right here shows the recommended value for a 1 gigabit per second link is 4, which is the default in classic spanning tree. But if you look at the link right next to it, it's the updated table. The original spanning tree was created in 1998, and the value that you could use for the cost was limited. In the updated version of spanning tree, you can see that the 1 gigabit per second link is recommended to be at 20,000 because it now scales for the much faster connections that just weren't around back in the day of the original spanning tree. Now, I want to quickly look at these other switches as well because I want to see if they are following what we think they should as their spanning tree path. I'll pull up suite 1, switch 2, that's .241, log in. Click on spanning tree, and what do we see? Look at this. Root port is set to lag 1. This is this switch's bridge ID, meaning it didn't win the election. It had a higher bridge ID than the root, which is suite 1, switch 1. So coming back to this, as we expect, RTST1 switch 2 is using lag 1 as its root port. Let's check out suite 4, switch 2. That'd be 10.225.1.243. Log in. And check out spanning tree. It looks like this guy is going through lag 1 as its root port. Now take a look at its path cost, 40,000. Now why is that? Well, look at the position of Suite 4 Switch 2. It's the only switch in this picture that doesn't have a direct connection over here to Suite 1. So based on what it was telling us, it said lag 1 is its root port, and it's seeing that as a cost of 20,000 plus the 20,000 that it costs Switch 1 right here to get all the way back to Suite 1 Switch 1. That's why we get this grand total of 40,000 as it's adding the two together. So what does that mean for this link right here? Well, we can assume that it is blocked. That's the one Spanning Tree had to block something to prevent a loop in the network. And based on where we see all these root ports, we can assume it's this link right here. But just so we can feel better, I want to see that. I want the switch to tell me what's blocked. Well, there's a couple ways we can see that. I've always been a command line guy myself, so I'm going to telnet into the switch and show you one way. 10.225.1.243, which again is switch 2 over here. Get logged in and do a show spanning tree. I can see the same output I could see from the graphic interface right here. It says the root ID, meaning the switch who is the root in my network, is this guy right here. This is his priority. This is his address. Remember, you combine those two things together to create the bridge ID, which the graphic interface does for us. And then I see, well, it's a cost for me, that is Suite 4 Switch 2, of 40,000 to reach that root bridge, and I go out port channel 1. Now again, Cisco made it a little pretty in the graphic interface and called it lag 1, but in the command line, this is what they refer to it as. It then says, this is me. I'm the bridge ID, blah, 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 with this priority and this MAC address. And then as I hit the spacebar, I see the status of all my ports. Right there is port channel 1, which is the root port. That's the one it goes to reach the root. And look at this guy. Gig 28. In our picture, that's this one right here, which we identified as being the blocked port. And sure enough, right here, it says this is a discarding alternate port. Now, if I was back in the graphic interface, I could have just clicked this link right below it, STP interface status, and I get a nice little pretty output right here where I can see gig 28 is our alternate or discarding port. That tells me that Spanning Tree Protocol has blocked that interface. The thing that I don't like about this output is it doesn't show me everything in one screen. I actually have to go to the interface type is a lag, and I hit go, and it refreshes, and then I can see, oh, okay, lag number 1 right there. That's the root port, and that's the one that's forwarding. It just bugs me. I like seeing everything in one place like it does in that command line output. Either way, whatever you prefer, that's how you can verify what's working with Spanning Tree. Now, there are two things that I want to bring up right now that we definitely want to correct with our Spanning Tree configuration. First off, this guy became the root bridge just by chance. I said it was a 20% chance with our 5 switches in our environment. That just so happened that he became the root bridge. I don't like that because if we bring another switch into the network, let's just say that this suite grows and we attach another switch right here, we're then rolling the dice that that one could become a root bridge, and then all the topology changes, meaning everybody blocks different links and ends up saying, okay, you are the center of the network. And that's bad because I don't want that switch to be the center of the network. That could be in somebody's cubicle. And by identifying it as the root bridge, all the traffic ends up going through it. And at a minimum, I have a subpar network performance. In a worst case, I cause a network outage every time Bob unplugs that switch in his cubicle. So how do I make sure that this guy is the root bridge? That's the first thing to change. The second thing is I know many of you remember our original switch design for this. And when you saw this blocked link happen, you're probably like, well, that's kind of lame. I wanted to be able to use that link. I don't want the entire Suite 4 having to share that one connection to go across. Can't I have this one be active and this one be active, and maybe we would have this one be blocked in this? The answer is yes, we can, but we have to tune Spanning Tree a little bit. You start to see why understanding Spanning Tree in the nitty-gritty detail is so essential. Let's have at it. I'm going to go back over to that switch number 1, which is over. Oh, we got logged out. There we go, log back in. I'm back on switch number 1 in Suite 1, which is our .240. This is the one I want to be the root bridge and stay the root bridge. The way I can do that is come underneath Spanning Tree and change that priority. Remember, the lowest bridge ID is the one who becomes the root bridge. Now, it just so happened that switch 1 in suite 1 became the root bridge because it had the lowest MAC address of everybody else. That's simply because everybody else's priority was set at the default, 32,768. They all tied. So they all said, who has the lowest MAC address? And that would be suite 1, switch 1. He said, that's me. But it leaves them vulnerable to some other switch coming in with a lower MAC address and preempting him. So the way that we fix that is to come in here and lower the priority. All you've got to do is lower it by 1 digit and you eliminate every MAC address from beating that number. But watch what happens when I hit apply. It comes up and says, whoa, whoa, whoa. Priority should be between 0 and 61,440 in steps of 4,096. What? Well, truth be told, Spanning Tree has gone through many revisions over the years, and they used to give you 65,000 some values that you could set. But someone along the way came and said, that's crazy. We don't need 65,000 values. Let's modify the protocol and do some other things with it. And it gets into VLANs and all that. We'll save that discussion for when we talk about VLANs. But what I will usually do when I'm saying I want this switch to be the root is come in and go, this will have the priority of 4,096. Apply. It says success. You might want to save your configuration. And look at that. Immediately, the bridge ID has changed. Let's just shoot back over to that suite 4 switch 2 over here, click on the status, and we can see that it's recognizing the root bridge ID is changing as well. It only takes a second or two for that to propagate through the whole switch network. That will keep some unconfigured switch from coming in and becoming the root bridge just because it has a lower MAC address. Now, it doesn't prevent somebody malicious coming in and trying to become the root bridge by setting their priority at 0 manually below your root bridge. But that gets into the security of Spanning Tree, which is a whole different discussion. For now, I like to keep it just at the core. So mission number 1 is accomplished. This guy will be the root bridge and it will stay the root bridge because we've set the priority to 4,096. Nothing else will beat that. But what about this one? I really wanted this switch to go this direction to reach this network. That way I can utilize both of these cables I have running between the offices. But instead, it chose to go this way as the root port and blocked this link. So 2 questions. Number 1, why did it do that? And number 2, how can I fix it? Well, let's first off talk about the why. And I've actually talked about this before, but it was in a little different situation. So let's apply it to our own. Here's suite 1 and suite 4. Switch 1, switch 2, switch 1, switch 2. We've got a lag here, and connections like this. This guy became the root bridge. So what's the first thing all the other switches do? They find their best way to get to the root. And switch 1 goes, oh, well, this way is the best way. Why? Because it has a cost of 20,000. And if I were to go this way, it would end up costing 60,000. 20 here, and 20 here. So man, this is definitely my best way. That's my root port. This switch also realizes it has 2 ways, but picks this way because that's a cost of 20,000 versus going this way, which would be a cost of 60. Same thing. This becomes his root port. But look at the dilemma of switch number 2. He goes this way and it costs him how much? 40,000. 20 here plus 20 here. Okay, that's path number 1. He goes this way and it costs him how much? 40,000. You've got 20 here and 20 here. He's stuck. How does he figure out which way to go? Well, do you remember this slide right here? Why does it feel so long ago that I talked about this? When a switch is trying to find the best path to the root, it's always going to try the lowest cost route. But what happens if it's tied? It's going to prefer the lowest bridge ID. So what does that tell us about our situation right here? We know that the root has the lowest bridge ID overall. I'll just draw a little low arrow right here. But in this case, suite 4 switch number 1 must have a lower bridge ID than suite 1 switch 2, right? Because in breaking the tie, our switch chose to go this way. That's why it chose that top route. That's why it ended up blocking that link. So then my question to you, how can we get switch 2 to prefer this way? Come on, think about it. Got it? We lower the bridge ID on suite 1 switch 2. Not lower than this guy because we don't want him to be the root bridge, but as long as we make him lower than this guy, this will become the preferred path. And what will probably happen then? The lag port will be the blocked port. Now, does that mean that switch 1 and switch 2 will have to go over to suite number 1 to reach each other? It absolutely does. But in our case, that's absolutely fine because we don't have any servers or anything sitting in suite number 4. Really, all they're going to do is use the internet connection over here in suite number 1. So it ends up working out better that way anyhow. We don't need a lot of communication between switch 1 and 2 and suite number 4. So let's do it. Let's head over to suite 1, switch 2, and lower the bridge ID and find out what happens. Oh man, I was talking too much and we got logged out. Suite number 1, switch 2 is .241. So let's get logged in there. Head over to spanning tree. Oh, not VLAN, spanning tree. And as we expect, we see the root bridge ID at this. Our bridge ID is this. Now we can't change our MAC address, that's burned into the switch, but we can change our priority. So let's set it one level higher than the root bridge ID. Now remember that error message that we got that said the priority should be between 0 and 61,000 in steps of 4,096. So one level above 4,096 would be 4,096 times 2. 8,192. 8192. Apply. And now we see that our bridge ID is 8192. We're not the root, we're still one step above it, but that should lower our bridge ID in such a way that switch 2 says this is now my preferred path to the root. Let's see if that happened. I'm going to head over to suite 4 switch 2, which is right here, and get logged back in. Click on spanning tree and look at the status right there. The root port is now gigabit Ethernet 28. Oh, I'm loving this. So previously the root port was lag going this way, and now it's saying, oh, nope, sorry about that. This is now my root port. I'm going this path to reach the root bridge. So let's verify. Does that mean that the lag is blocked? Let's click on the STP interface settings, change the interface type to lag, and click go. And look at that. Our theory is proven true. Lag 1 is considered the alternate port in a discarding state. That is awesome. Now, I told you that you will be able to understand and configure Spanning Tree Protocol like a ninja. In order to achieve that ninja-like status, you may have to, number 1, go back and watch this again. I went through all the concepts and then I applied those concepts in our very real environment. The second step of becoming ninja-like is to do this yourself. In your lab environment, I want you to elect a root bridge and then determine which ports are forwarding and blocking and create a spanning tree map of the network. Do you remember back in the Nugget when I talked about documentation? That's one of the things that I said was a very useful thing to have, a spanning tree snapshot of the network so you can see what your real topology looks like. And you can be that much faster when troubleshooting issues that could arise in the network. All the spanning tree map does is show which ports are really active. Let's say you had a network that was this big, all these switches connected together. Obviously, there's going to be a whole bunch of links in there that are blocked. Thus, a spanning tree map is redrawing that same topology, showing which links are actually active. That way, if something is going wrong, you can go straight to the link that has the problem instead of going, oh, nah, that one's blocked. Oh, nope, it's not that one. That one's blocked too. That is what Spanning Tree is all about. I hope this has been informative for you, and I'd like to thank you for viewing.